And this is the Statics Zoom for Friday, April 24th. And we're going to go over a lab experiment that I wish we were in person showing you this, but this is the next best thing to being there, as the phrase goes. And it's ground freezing. Okay. So this was a phenomenon that I had not really seen or heard about until about 2010. And we went on a moles trip down to Sunnyside Rail Yard in Queens. And this was the East Side Access Project, where they were going to extend the Long Island Railroad from Sunnyside Rail Yard in Queens over to Manhattan. So we got to see this a couple of years in a row, and it was just a phenomenal project. The main part of the project was establishing this early access area, which is right here, kind of what they call a cut and cover. So they're going to literally use what we call support of excavation, SOE, again, support of excavation in this area to create a launching area for what's known as a TBM, which is a tunnel boring machine. And then the tunnel boring machines would drill over to the Grand Central Station to create some new lines. And again, the extension of the Long Island Railroad over to Grand Central. They were literally putting the new tunnels below the existing tunnels at Grand Central. Here's a shot of a TBM. Slightly bigger than the biggest drill bit that I have here at home. This is about, I think, a 20 or 21, 22 foot diameter drill bit, if you will. And it's basically going to drill through rock that you see right here. So again, that was most of the project. This is the where they call the TBM launch, where they set up the TBM. We may do another lecture on this someday, but I just want to give you a little bit of a feel for the main portion of that project. So again, what you just saw was launching the TBMs at this point. And another part of the project was a connection of this area, this launch area, underneath Northern Boulevard to another rail yard over on the opposite side of Northern. That was about, I don't know, maybe 600-700 feet. And it was just too short of a distance to use the TBMs. And it also was an area that did not have rock. And if it did, it was weak. And again, this is about 10 years ago, so I'm trying to remember why. But the easier part was to use a phenomenon called ground freezing to go underneath an existing subway. So this is the cut and cover that you just saw. This wall, I'm not sure if that existed, but this was the open access area. And here's Northern Boulevard, existing Northern Boulevard, an existing subway under Northern Boulevard, and an existing L, which we always, in Chicago, they talk about the L, which is the elevated track. So another mass transit subway, if you will, above ground. So they had to extend from the cut and cover underneath Northern Boulevard, underneath a subway, and underneath an elevated track. They had to put a tunnel underneath that. So what they used is a ground freezing technology. And it just, to this day, it blows my mind. I remember the first time meeting some of these folks at the site. I was watching this, and the first words out of my mouth is, "You guys are shitting me." So shouldn't have said that either now or then, but it is pretty phenomenal. So we got thinking. I asked the engineers, I said, "Can I have the calculations for that?" And they kind of laughed at me, and they said, "Well, no, it's proprietary." In other words, there's big money in this technology. to go to the website, take a look at some of the ground freezing. There's some really cool pictures on the web that I've put on that PowerPoint. I won't publish the PowerPoint, but I did put the data sheet on with a couple of photos for your use. One of the things that was interesting that they did, and I believe this was at the Fukushima Japanese nuclear reactor that was damaged in a tsunami years ago, and they wanted to cut off some of the groundwater around it. And so they've gotten into ground freezing, and for the life of me, I can't find those photos. I know they're in here. So I'm just going to scroll down through here. Yeah, let's see. Here's a good oh, here it is. So this was the Fukushima nuclear reactor containment. And so in essence, what they did was create a frozen soil blanket around the reactors to try to prevent groundwater flowing from the hillside and getting contaminated. So that's one of the uses. Another project that we toured in New York City, and I got to find the another one was the 2nd Avenue subway, and I think that was from in the 60s, 60th Street up to the 90s. That was tunnel boring machines going through some good Manhattan rock, and all of a sudden they realized that the rock had actually dipped. So imagine this bedrock, if you will, instead of being at this elevation, all of a sudden it's at this elevation. It's just something that they did not foresee. So what they did there is they froze vertically. Okay, now what we're going to show here also at the Fukushima nuclear reactor, they drilled vertically. At the Long Island Railroad at Queens, they were drilling horizontally, which we'll go over in a minute. But what they did in, see if that comes through for me. Nope. What they did there was they drilled vertically for the 2nd Avenue subway, and then they were actually able to bore through the frozen soil with a TBM because they'd already, 90% of their work, 95% of their work was done with the TBM. I'm not sure if I'm getting my percentages right, but I do know that ground freezing was used on that. So I got thinking, they're really, I got thinking about what we could do for our lab. And so we used a Proctor mold, which is a 4-inch diameter mold that we use for soil compaction. We compacted some clay. I figured that'd be the easiest one. And we compacted it in that mold, and then we extruded it. We literally jacked it out of the mold. And this is the sample before we put it in the compression machine. Well, then we jacked it out of the mold and immediately froze it. And then we kept it in the freezer for a couple of days. We made a sample for each of the labs. And then we, I got to manage the participants here. Okay. So then we extracted it and we put it in the mold, or the compression machine in Lab 18. And so this is what it was doing. Now this is going to be 6 minutes. I'm not going to bore you with 6 minutes. Oh, there's my. And what we're going to do is we're going to talk about the loads that were involved and how we calculated the stress that frozen soil can withstand. Our numbers were much lower. I talked to folks in industry, and our freezer in Smith Hall wasn't doing that well. I had put it in the freezer. It was frozen. But I also had some pierogies that I bought from the mechatronics faculty, and they were not totally solid, so I knew that the freezer was not working right. So you can see the ice lenses starting, as it's starting to thaw, not just from room temperature, but from the energy as we're squeezing the living you-know-what out of that sample. Again, it's, what do you think the load would be on that? Any guesses? Give me a number, somebody. Anybody awake?
50,000.
Yeah, that's a little high.
30,000.
20,000.
Geez, you guys are, you got a lot of confidence in me. Wasn't it?
5,000.
Yeah, it's about 5,000. So that's the video of it. And then we got, this is what it looked like. You could see that it was just starting to squirt out the top and bottom of those end caps that we used. And then there's a picture of it at the end. So it was pretty interesting stuff. So what we did is we started out with clay, and then just for the hell of it, I thought I'd use some play sand. I had bought that for a soil test, the sand cone. Some of you remember that from soils. And so it literally was just a uniform sand from one of the stores around here, bagged sand, and it literally is play sand. So what we did is we put it in a 4x8 cylinder, and then we just compacted it a little bit, and then we saturated it. So we kept adding water till we had it saturated, and then we froze it. So that was the second soil type, if you will. And then one of the students had a great idea. He said, well, what does ice freeze at? I didn't have a clue. So I said, well, that's a good idea. So what we did is we froze some ice. I thought I had pictures of that. I thought I had a video, and damn it, I can't find it. And I can't get in the lab to run the test again. So you'll just have to believe me. And that year, I think we just used tap water. One of the students thought it would be a good idea to use boiling water to boil it. And then another student had a great idea to use, oh heavens, distilled water. So this one was just regular tap water, I believe, from from Smith Hall. And so what you're going to do is you're going to show all the calculations for the clay sample and the ice sample. But you're going to have to show all the data for the play sand as well. And that's what we're going to go through right now. And again, you've got the Excel that you can use in Vanco Hall. Now, this has not been updated, but there is, when you go to that, you'll see that it's under frozen soil. So let's go to Vanco Hall, and Excel. Is there any Excel here? Oh, let's go to the top. Statics e-files. There it is. Now, this one has not been updated with what you're going to see now, but you can still use it because it still has that, whoops, that's not it. It still has this, again, frozen soil. So go right to that, and we'll start to run the calcs right now. So the clay, the first thing we had was, the clay was 3-inch diameter. And so that's automatically burps out the area. Okay. I believe that the XLs that you have, which are up here, yeah, I used 22 divided by 7. I'm not sure if, because I couldn't remember how to put pi in there, full disclosure. But here's some of the data that we've done in the past. So again, you can use the Excel. When you enter the diameter, it gives you automatically the cross-sectional area. So on the homework, you've got to show that, that calculation. In other words, you've got to show the strain, which we'll go over, the cross-sectional areas, and the stress, and also actual stresses. Let's and I'll update this. And actual compressive stresses. And modulus of elasticity. Which is E. Okay. For the, and we got to spell that right. Okay. So let's do that. Okay, so you're going to show the calcs just for the clay, just for the ice. You're going to show the strain, which is change in length divided by original length. We're going to give you the loads, and then you're going to have to calculate cross-sectional area, show the calcs for the stress, and then show the calcs for the modulus of elasticity. Okay. So if we go to, I'm going to go back to the Excel. That's not it, damn it. Okay. And here are the numbers that we had the change in length. And again, I wouldn't say that all of these are, I would not say that all these are incredibly accurate. If you look at this, the change in length, which was quite extensive, it actually compressed 3.75 inches. And so stress over strain, if you go to JN's notes on page 64, strain is the strain, not strange, the strain is the change in length divided by the original length. Okay, so you got to show those counts, but there's the formula for you, right? So it's this D53 divided by cell C53. And the load on that was 7,000 pounds. Okay. And that's going to give you your stress. Again, there's your stress is equal to load, which is cell F53 divided by the cross-sectional area, which is G53. Okay. And we'll put these all in the middle so it looks a little nicer. Well, then we took the play sand. Now we did 2 of those. We only did a change, a strain dimension or strain measurement for one of them. So you've got to put in the data, which we're going to do for you. So here for this sample, and these were 4-inch diameters. Makes sense because that's the same as a concrete cylinder, right? The 4x8s. And that should make sense. It was 12.57, 0.5664 for cross-sectional area. And the play sand at 5,000 pounds, I couldn't believe that well, what we did is it moved about 1/8 of an inch. Okay, that was it, about 1/8 of an inch. Now it's interesting that when you talk about that, and what they did is they put monitors in these subways, they put monitors on the L, so that as they were putting in this tunnel, they were monitoring any change, right? Any settlement due to the fact that they were tunneling underneath that soil. This blanket of frozen soil was 6 foot thick. It just absolutely amazing. So again, going back to here, this was the cut and cover, the early access chamber. And that's a schematic of it. So in this area, there's your Northern Boulevard. There's a subway underneath. There's your L. They're looking this way, is looking this way. So that's the actual early access chamber. This is cross-slot bracing. This is diagonal bracing. And this is what's known as a slurry wall. Okay, and we'll talk about that someday. So that the drill rigs that you're going to see in the next picture are way down here. And here they are. They're drilling horizontally. And so the drill rig's right here. So they're drilling horizontally, a series of pipes, if you will, piping. And then they put the refrigerant through, and they literally create a doghouse cross-section 6 foot thick that's going to support, if you can believe it, the subway, Northern Boulevard, and the L. So there's your simulation of the drill rig right here. Actually, the drill rig is right here. Okay. So let's see. And then what they did is they did what's called segmental excavation. So they don't have slides for all of it, but you can see the sections right here. So they would excavate sections out of the frozen soil. And one of the pictures from the web, this one, was interesting. Really shows the this frozen soil up here. You know, ambient air is starting to make it look that color, but here they're excavating through the frozen soil. Here is a picture of their freeze pipes. This is a much smaller application, liquid nitrogen tank, if you will. So again, they're doing segmental excavation. So they would excavate this part out underneath this blanket, this igloo, if you will, igloo cross-section of frozen soil. And then they would put insulation against the frozen soil and use shotcrete. And shotcrete, if you can imagine a fire hose, instead of shooting out water, it's actually shooting out concrete, if you will. A very small aggregate. And then under pressure, again, why did they put insulation against the frozen soil? Because if they shoot concrete against frozen soil, the concrete will not cure. So as they did, say, this segment, they got in there and they put insulation against the frozen soil. Then they tied in like a welded wire fabric for the shotcrete to bond to, give it reinforcing. Shotcreted, I don't know how thick the layer was. And then that became, eventually, they would do that at each part of the segmental excavation. So they would take care of this right here, and this part of the tunnel right here, and this part. And so eventually, when they got that all done, right, this was all shotcrete, it looks way too smooth because this is actually the final tunnel. But once the shotcrete was done, then they put in panels, precast concrete panels that go together like an erector set that creates the tunnel. Okay. And then there's always a gap between the precast concrete tunnel sections and the rough shotcrete. And so what they do is they pressure grout any annular or any gaps, any annular spaces or gaps between the precast tunnel sections and the shotcrete. Okay. So I'm going to make myself a note here. I should have had a slide on shotcrete. Okay. And then eventually, like I said, this tunnel connected the East Side Access main area at Sunnyside Rail Yards with another rail yard on the other side of Northern Boulevard. So let's go back to the calcs, and then you folks can ask me any questions. So that was 5,000 pounds. And this was actually you can see it's equal to 1/8 of an inch. Okay. It's so 1/8 of an inch divided by 8 inches. That's its strain. And then there's its modulus of elasticity in PSI. And again, I know these numbers are low.
Wait, so we're not filling those in?
Yes, you are.
We are? All right.
Yeah. You're filling in everything. We're just doing it for you here, but you got to show calcs for the clay and the ice. So that was, in other words, we held the load at 5,000. We measured what the compression of the 8-inch mold was. It only compressed 1/8 of an inch, the change in length, or you could say the change in height. And then we loaded that son of a, almost said it. We loaded that thing to failure. And to this day, I can't believe that it held close to 16,000 pounds. Play sand, just amazing. Frozen play sand held close to 16,000 pounds of load. So you won't be filling these in because there was no data taking on the change in height. We just loaded that till it failed. But what you can see is that it had an actual stress of 1,200 PSI. So that was pretty good. That was some pretty good results. Again, just on play sand. And then the ice. And the ice held 5,500 pounds. Was amazed again at what that could do. Now, why is the cross-sectional area not working? Because I have not put in the diameter. And that was, again, a 4-inch diameter. It was a plastic mold that we used for the concrete cylinders. The length, I didn't fill it all the way to the top. I just filled it a little over 6 inches and put it in the freezer. So once we burp that diameter in, there it goes. So we can show the calcs. And that's pi d squared over 4, which is consistent with what we've talked about since day one with units. Okay. So it had an actual stress of 437.7, PSI. And then it also had a strain, and we could calculate the modulus of elasticity, which is a measure of the material or cross-sectional stiffness. Which one? Anybody?
What was the question again? Sorry.
Woof. Okay. Modulus elasticity is a measure of material or cross-sectional stiffness.
Material.
Material.
Okay. So that's, like I said, that's another really cool application of strengths of materials for ground freezing, which again was just, I was in awe. I didn't want to leave that day. Plus they had the best damn donuts I've ever had. And I've actually got a picture of that somewhere. I think I need to show you that. That's important. I got a couple of, so that would be under heavy civil. And these are some SOE methods. This is called, actually I'm on a dead end road and somebody just drove by, so it's so boring here I had to wave. Sorry about that. This is called a soldier pile. Maybe I'll throw this on the, I'll do a PDF of this. This is the slurry wall. If you take a look at this, those are the donuts. Just unbelievable at the Moles trip every year. So I had to take a picture of it. And then this is the slurry wall. This is the clamshell digger, clamshell bucket. Basically what you do with a slurry wall is you put up concrete guide walls, right? And they're big, they're humongous. And what you want to do is this is like a, what they call a supportive excavation if you're going to put a building on one side. And write myself a note. So SOE.
I think we did this in the beginning of the semester.
No, this is a board at, it was 125th and Broadway. Columbia University was putting in a brand new building. So
Yeah, but I think we did this PDF in the beginning of the semester.
did we? Okay.
Yeah.
Oh, just humor me. And so there's the guide walls right there. And then the clamshell bucket right here is this. And then you dig down as deep as you want to go. And as you're digging down, you're adding a slurry, which looks like cream of mushroom soup. This machine is used when you get down into rock. Because if you look in this cross section, you want to put a keyway or a socket into rock. So then you basically have a whole trench of cream of mushroom soup, a bentonite slurry, and then you're going to put in a rebar cage in that. And that's another type. Here's a slurry wall up at the Syracuse project that we toured a number of years ago. So this deep stick excavator, right? It's like picking your nose. I think yesterday was National Nose Picking Day. I'm not making that up. I heard it on XM radio, so it's got to be true. So here's the piping that's adding that slurry in, and that's how deep they're going. Okay, these are pictures of sheet piling, right? And then whalers, cross-lot bracing, really phenomenal projects. And there we are after a Moles trip way back in the day. And this was down at the Fulton Street subway project. So again, just a lot of cool projects that you can get into. So what's due? Okay, this data sheet has been posted to Vanco. I will update it because you got to throw some modulus of elasticity calcs in there. Put your calcs right here for me. Show me all your calcs. And since our next Zoom is Tuesday at our regularly scheduled time of 6 p.m., we'll have this due Monday night at 11:59 p.m. So another easy 12 points for you. I think we got about 6 weeks left. We're going to go into middle of June, maybe first part of June. Somebody's awake. Just seeing if at least you're not like the freshmen. They got mad at me. Not really. I just had to say that. Am I still recording? Jesus, I am. Sorry about that. So what we're going to talk about on Tuesday is we're going to get into beam deflection, which you're going to use a lot in structural theory. So let me just take a look at my notes. Oh, I've got some reading for you that we need to do for Tuesday Zoom. Okay, here's the reading. I will update that ground freezing data. Here's the drop box for the ground freezing calcs. And we'll go from there. And then we'll do a deflection lab. We'll talk about that. And then we'll talk about another lab where we simulated the deck failure of the ledger beam. We'll talk about that, and maybe another lab or two. But we're, including finals week, I believe we only have 3 weeks left, which it's interesting. It's gone slow, but it's gone fast. This course will be given final grades. My other 2 courses have lab components. This lab component for statics we're able to do in lecture. So the final grade you get is the final grade. There won't be any what we call in progress grades. And I think I got to get grades done by the 18th. So, so any questions? Okay, so what I'm going to do is I'm going to stop recording. This is the end of Zoom for Statics and Strengths of Materials, Friday, April 24th. And we'll come back next Zoom Tuesday, April 28th, same bat channel, same bat time. That's from the Batman show in the 60s. And then we will post it to YouTube.